let's build on a previous investigation. Previously, we built these 3 circuits. We closed the switches and we found these current strengths. The question we were asking was, how does number of resistors in parallel affect current strength in the main part of the circuit? And we found that as we added more resistors in parallel, the current strength in the main part of the circuit increased. Our conclusion was, adding resistors in parallel increases I main. I main is the current strength in the main part of the circuit. And our explanation of why this is so is that as we add more resistors in parallel, that decreases the total resistance of the circuit. And the reason for this is that adding more resistors in parallel gives more paths for the current to flow through, and so it makes it easier for the current to flow in the circuit. If it's easier for current to flow, the resistance of the circuit is less. But now let's change our question to check if this is really true. Let's rather ask, how does total circuit resistance in a parallel circuit affect I main? So you see what we've done? We've changed our independent variable from number of resistors in parallel to rather being total circuit resistance in parallel. How do these two differ? In the previous question, number of resistors in parallel was the independent variable. So for this circuit, there were actually no resistors in parallel, but we might say there was 1 resistor there at least, together with a bulb. In this one, there were 2 resistors in parallel, 3 resistors in parallel. But now our question is, how does total circuit resistance affect I main? So our independent values are now not 1, 2, and 3, but rather something in ohms. So what is the total circuit resistance for each of these circuits? We'll have to calculate that. And the first step in calculating that is we have to convert each of these circuits into an equivalent series circuit. Now the first circuit is easy because it is in any case a series circuit, so we don't need to do anything. But for the next 2 circuits, what we need to do is to find the equivalent resistance which can replace the parallel branch, so that we replace the parallel branch with an equivalent single resistor in series with the bulb. How do we do that? Remember that we can calculate equivalent resistance for resistors in parallel using this formula. 1 over Rp, which stands for 1 over the equivalent resistance for the parallel branch, equals 1 over R1 plus 1 over R2 plus 1 over R3, or however many times you have to continue, where R1, R2, R3, however many R's you need, refer to the resistance of the resistors that are in the parallel branch. If we only have 2 resistors in parallel, then the equation that we've just previously looked at simplifies to this equation here. The equivalent resistance of the parallel branch is equal to the product of the 2 resistances that are in parallel with one another divided by the sum of the 2 resistances. R1 times R2 over R1 plus R2. This only applies, though, if we have 2 resistors in parallel. For 3 or more, we cannot use this simplification of the equation. So we need now to calculate what the equivalent resistance is of this branch and what the equivalent resistance is of this parallel branch. Pause the movie until you've done that yourself. Let's start with this one, which has 2 resistors in parallel. Because there are only 2 resistors in parallel, we can use the simplified form of the equation. Rp equals R1 times R2 over R1 plus R2. Both R1 and R2 in this particular case have a value of 10 ohms. We substitute into the equation 10 times 10 divided by 10 plus 10. 10 times 10 is 100, 10 plus 10 is 20, 100 divided by 20 is 5, and the unit is ohms. And we actually didn't even need to do this calculation because it's obvious. Here we have 2 resistors in parallel, each having resistance of 10 ohms. Their combined effect is as if they make a double as thick pipe as what they were individually. A double as thick pipe is half as resistant. So their combined resistance is half as much as each one's individual. Half of 10 is 5. So we can replace these 2 10-ohm resistors that are in parallel with one another with a single resistor of value 5 ohms resistance. And we have converted this parallel circuit into an equivalent series circuit. that. Let's just confirm that we would get the same answer if we rather used the long version of the equation. 1 over Rp equals 1 over R1 plus 1 over R2. We substitute 10 ohms into R1 and R2. 1 over 10 plus 1 over 10. That equals 2 over 10, which is the same thing as 1 over 5, 1/5. Now be careful here. That does not mean that the equivalent resistance is 1/5 of an ohm, because remember this is equal to 1 over Rp. So we need to invert the answer to find what Rp itself is. The inverse of 1 over 5 is obviously 5. So the equivalent resistance is 5 ohms, which is what we'd already seen using the simplified version of the equation. But now we can see it doesn't matter which equation we use, we get the same answer. Let's move on now to the third circuit. What is the equivalent resistance of 3 10-ohm resistors in parallel with one another? Now we have to make use of the long form of the equation. This form will not work because now we don't only have 2 resistors in parallel, we have 3. So we have to make use of this equation here. We substitute 10 ohms into R1, R2 and R3. 1 over 10 plus 1 over 10 plus 1 over 10 is obviously 3 over 10. We invert that to find the equivalent resistance Rp rather than 1 over Rp. The inverse of 3 over 10 is 10 over 3. And 10 over 3 in decimal is 3,33. So 3 10-ohm resistors in parallel with one another has the same effect as a single 3,33 ohm resistor. So here what we've done is we've converted each of these circuits into their equivalent series circuits here. And we can now use these equivalent series circuits to help us answer our research question. We're trying to find out, how does total circuit resistance for parallel circuits affect I main? To do so, we replace these original circuits that are in parallel with their equivalent series circuits, and then it's easy to find the total circuit resistance of each of the circuits. Let's prepare a table into which we can put our data. How should we write the heading for the table? How should we write the headings for each of the columns in the table? Table showing the relationship between total circuit resistance in parallel and current strength in the main part of the circuit. So total circuit resistance in parallel is our independent variable, but I'm going to shorten that to total circuit resistance. Its unit is ohms. And current strength in the main part of the circuit is our dependent variable, but I'm going to shorten it in the table to I main, and its unit is amperes, A. But now we still don't have the total circuit resistance. We've converted each of the circuits to a series circuit so that it's easy to get the total circuit resistance, but we still need to get the total circuit resistance. How do we do that? The total circuit resistance for resistors in series can be found simply by adding the resistance of the resistors. So in the first circuit we have a 10 ohm bulb in series with a 10 ohm resistor, so the total circuit resistance is simply 10 plus 10, 20 ohms. In the second circuit we have a 10 ohm resistor in series with the equivalence of a 5 ohm resistor, so the total circuit resistance is 10 plus 5, 15 ohm. And in the third circuit, 10 plus 3,33, 13,33 ohms. We put those values into our table. So now we have our independent variable values. We need to get the current strength values, and we've actually already done this. Remember, we found that for the first circuit the current strength was 0,45 amps, the second 0,6 amps, and the third 0,67 amps. So we put that into our table. And what do we notice? Can you see that as we go down the table, the total circuit resistance is decreasing? Just remember back that that corresponded to an increase in the number of resistors in parallel. Here we only had one resistor. There were 2 in parallel, and there were 3 in parallel. So although the number of resistors increased down the table, the total circuit resistance decreased, which is what we discussed previously. And then the next thing to notice is that as that total resistance decreases, the current strength increases. So we have the highest current strength where we have the lowest total circuit resistance, and we have the lowest current strength where we have the highest total circuit resistance. So this shows an inverse relationship. When one is high, the other is low. Is it an inverse proportion? Inverse proportion means that as the independent variable is increased, the dependent variable decreases by the same factor. This is an example where the independent variable is high, the dependent is low. Where the independent is low, the dependent is high, which is what we've seen in our data, but is it by the same factor? To check that, an easy thing to do is to simply multiply the independent and dependent variables by one another, and if we get a constant, then we know that the two are inversely proportional to one another. In this particular example, the constant happens to be 5. It doesn't really matter what the constant is, but the fact that there's a constant shows that these two sets of numbers are inversely proportional to one another. So let's check that out. Let's multiply the two variables by one another and see whether we get a constant. Pause the movie while you do that. 20 times 0,45 equals 9. 15 times 0,6 equals 9. 13,33 times 0,67. Now notice that doesn't give you exactly 9. Had there been no rounding off, we would indeed have found exactly 9. Because we are aware of the error that we have, we round off so that the error does not distract our attention from seeing the pattern. What do we see? Indeed, we get a constant telling us that these two are inversely proportional. And anyway, this is the same relationship as we've seen in a previous movie where we investigated the relationship between resistance and current strength in a series context. It doesn't matter whether we're speaking in a series or a parallel context. If we take the total circuit resistance, it is always going to have an inverse relationship to the current strength through the main part of the circuit. More than that, R times I equals in this case 9. What's special about 9 in this particular circuit? Remember that we used 9-volt batteries in each circuit. So resistance times current strength doesn't only give us any old constant, it gives us a very specific constant, the voltage of that particular circuit, which in our case here happened to be 9. Now let's plot a graph of this data. Resistance is our independent variable, it goes on the x-axis. Current strength is our dependent variable, it goes on the y-axis. The heading is graph showing the effect of resistance on current strength. And sure enough, we get this kind of a shape which shows us that we have inverse proportion between the two variables. And we have again shown that there's this relationship between these variables. Resistance multiplied by current strength gives voltage. Or if we give that in units, ohms multiplied by amperes equals volts. So what is our question? How does total circuit resistance in parallel affect the current strength in the main part of the circuit? Or we can just simplify it to be, how does resistance affect current strength? Because total circuit resistance, once we work it out, has nothing to do with it being a series or a parallel circuit, because we convert the parallel circuit into its equivalent series circuit. So instead of saying total circuit resistance in parallel, it really makes more sense just simply to say resistance. And then similarly, we don't really need to say affect current strength in the main part of the circuit, because what's in the main part of the circuit is actually flowing through all the circuit. It's just that as it goes through the branches it splits up, but the sum of it is all still the same. So we can just simply say, how does resistance affect current strength? And what is your answer to that? It's the same answer as what we got in a previous investigation where we looked at it in a series context. Give it in this form. The dependent variable is inversely proportional to the independent variable. Current strength is inversely proportional to resistance.